I welcome all of you in second session on complex numbers topic. So in first session, we have studied definition of complex number and we have talked about the concept of operations like addition, multiplication, division, etc. on set of complex number, and we have also studied their properties. Now, one more operation I forget to explain, that is nothing but equality operation. Equality of two complex numbers. So Z is equal to A plus IB and W is equal to say C plus ID belongs to C are equal if and only if the real parts are equal and imaginary parts are equal. A equal to C and B equal to D. Then we say that two complex numbers are equal. Two complex numbers are equal. Here we are talking about equality of complex number. Two numbers, complex numbers are equal if their real parts are same and imaginary parts are same. Now actually complex number A plus IB, if complex number described by two numbers, real numbers A and other say B, and then A plus IB, if I draw the perpendicular on x-axis through A and perpendicular on y-axis through B, then what this intersection point of that two lines will get, it is nothing but A plus IB complex number. So for this complex number A plus IB means complex number is represented by point in a plane. This is called as imaginary axis. We will take the imaginary part on y-axis and this is called as real axis for the complex plane. Actually it is your xy plane. Why I am explaining this here? Firstly, for two real numbers A and B, this is your real line and this is your complex plane now. This is your complex plane. If I take two real numbers, A and B belongs to R. If A is on left hand side, B is on right hand side on real line, then A is less than B. A less than B. So for two real numbers A and B, we say that A is less equal B if A lies on left side of B. Equivalently, A is less equal B if and only B minus A is greater or equal 0. B minus A greater or equal 0. Now for two complex number A plus IB and W is equal to C plus ID, I cannot compare these two numbers. I cannot compare that two numbers. Here is C plus ID. So for this, your A and C are equal because the real part lies on same line. So A equal to C but B not equal to D. B not equal to D. Imaginary parts are different. If I take number here C plus ID, then your imaginary part B and D must be equal to B, but C is not equal to D. C not equal to D, and that's why it is impossible to say one complex number is other than second complex number. So less equal relation is not defined on set of complex numbers. We cannot compare two complex number by less than or greater than relation. So only equality relation is there, and this is the basic difference between set of real number and complex number. On set of real number, I can compare two real numbers, either they are equal or one is less equal, one is strictly less than other. That is possible. For complex number, we can only talk about equality of complex numbers, but less than concept is not defined for complex number. So if I have two complex number 2 and 3 belongs to C, in R 2 is less than 3, but for 2 3 belongs to C, 2 is not less than 3, 3 is not less than 2. So order relation is not defined. This is basic difference in set of real numbers and complex number. So remember this in mind, and that's why firstly I am explaining why it is impossible to define order relation on complex number. So order relation is not defined, while in set of real number order relation is defined. Equality hold in set of real number as well as in complex number. Okay, so this is the basic difference between the two sets. Moreover, plane representing complex numbers is known as complex plane, where representing that numbers in xy plane itself, in which y is called as imaginary axis, x is called as real axis, and plane representing complex numbers is known as Argand's plane. Argand's plane. 0, 1, 2, 3, so on, 1, 2, and so on. If this is representing a plus ib complex number, then this plane is called as complex plane or Argand's plane. Okay, so what is Argand's plane? Plane in which complex numbers are represented is known as Argand's plane. Okay, now we'll take examples on operations on complex number. Operations on complex number. So take the example, say first one, simplify square root of minus 16, and write anything here whose square roots are known to you. Square root of minus 25 plus 4 times square root of minus 49 plus or minus 5 times under root of minus 256. So square root of minus 1 is I, so this is I times, and square root of 16 is 4, so this is 4I. Likewise, square root 25 is 5 and square root minus 1 is I, so it is 5I. This is 4 times square root of 49 is 7 minus square root 7I minus 5 times square root of 256, 16I. And then you can easily simplify it. It is nothing but 9. Okay. minus 80I, right? So 80 minus 37I is nothing but 3 carry 1, 8 minus 4, 43I. Okay, so in this way, just by using definition of square root of minus 1 is equal to I, you can solve such type of examples. So there are so many examples of this type in your textbook. Go through that examples. Now we'll take next example. Find AB belongs to R such that A minus B plus A plus BI is equal to, say, A plus 5I. Now A and B are real numbers, means A minus B itself is a real number, A plus B is a real number. Now means this is the real part, this is real part, this is imaginary part, this is real part, this is imaginary part. So by equality of complex numbers, okay, by equality of complex number, we have two complex numbers are equal if and only if their real parts are equal. So A minus B is equal to A and A plus B is equal to 5. What to solve these two equations? So your first equation, adding minus A on both sides, will get B equal to 0. Substituting B 0 here, A plus 0 is equal to 5. And therefore, A equal to 5, B is equal to 0. This is the way of finding real numbers for such equations. Take next example. Find AB such that AB belongs to R again. R such that A plus B into 2 plus I is equal to, say, B plus 1 into B plus 10 plus 2A I. Okay. So again here this is your real part. This is imaginary part because A and B are real numbers. So B plus 1 must be real number. 10 plus 2A is a real number. But here first you have to simplify this. So this is equivalent to A plus B into 2, 2 into A plus B plus I into, or A plus B into I is equal to B plus 1 plus 10 plus 2AI. Now this is real part, this is imaginary part here, this is real part, this is imaginary part. Comparing real and imaginary parts. Real and imaginary parts on both sides. We get 2A plus 2B is equal to B plus 1, and second equation will become A plus B is equal to 10 plus 2A. Simplifying this, taking B on this side, we will get 2A minus B is equal to 1. Then taking 2A on this side, A minus 2A is minus A. So minus A and plus B is equal to 10. Adding these two equations, B minus B get cancelled, 2A minus A becomes A is equal to 11. Substitute A equal to 11 in any one of these two equations. So minus A plus B is equal to 10. Therefore, minus 11 plus B is equal to 10, and therefore B is equal to 21. Therefore, what is your solution? A equal to 11, B is equal to 21. You are well familiar how to solve two equations in two unknowns, and we are just doing this one here. Now, if I take example, say ABI is equal to, again find two numbers A and B, real numbers, such that ABI is equal to 3A minus B plus 12I. So this is equivalent to 0 plus ABI is equal to 3A minus B plus 12I. So this is your real part here. This is imaginary part. This is real part. This is imaginary part. So two sides are equal if and only if their real parts and imaginary parts are equal. This implies 3A minus B is equal to 0. And AB is equal to 12. AB is equal to 12. This is 1, this is 2. So from 2, product of two numbers is 12, which is not 0, means A and B must be non-zero numbers, and therefore B equal to 12 by A. Use 3 in 1. Using 3 in 1, we get 3A minus 12 by B, 12 by A is 0. Simplifying this, we will get 3A square minus 12 is equal to 0 into A, that is 0. And therefore, taking 12 on that side, we will get A is equal to 4, and therefore A is equal to plus minus 2, taking square root, which implies B is equal to 12 by A, which is equal to, if I divide it by 2, we will get 6, and my minus 2 will get minus 6. Therefore, we have two solutions here. Therefore, we get A equal to 2, B equal to 6, or A equal to minus 2, B is equal to minus 6. There are two solutions. Now, Solve the equation 1 upon a plus ib. Next example, 1 upon a plus ib is equal to, if I take any number 5 minus 7i, say 5 minus 7i. So this is equivalent to, taking reciprocal on both sides, we will get a plus ib is equal to 1 upon 5 minus 7i. Okay. Or taking a plus ib on that side, 5 minus 7i on this side, we will get this one. Now in this example, if denominator contain I term, then multiply numerator denominator by its complex conjugate. So what is the complex conjugate of 5 minus 7i? For complex conjugate, always change sign of imaginary part only. So multiply it by 5 plus 7i upon 5 minus 7i into 5 plus 7i. So this is equal to 5 plus 7i. A minus b into a plus b gives us 5 square minus 7i its square. So that is 5 plus 7i upon 25 plus minus or plus 49. Since I square is minus 1. I square is equal to minus 1. Or you can take, use formula for z is equal to a plus ib complex number or x plus iy. Z into z bar is equal to x plus iy into x minus iy is always equal to x square plus y square. Till I have not talked about what is meant by modulus. But if I represent this complex number in plane x plus iy here, that is pair xy, then if it is point P, then distance of this P from origin r is equal to, this is exactly under root of x square plus y square. X square plus y square, and this r is known as mod of z. So this is nothing but mod z square. Till we have not talked about what is meant by modulus. Modulus, okay? But mod z is nothing but distance of that complex number from origin in complex plane. Okay, so for z equal to x plus iy is distance. Mod z is under root of x square plus y square. It is just by distance formula. 0 is 0 plus 0i. Z is equal to x plus iy. If I represent them by order pairs 0, 0 and xy, by using distance formula, we will get OP is equal to under root of x minus 0 square plus y minus 0 square, which is under root x square plus y square. Okay, so you can use that also here. Now our aim is to simplify this, which is simple one. So what we get? 5 plus 7i upon 9 plus 5 gives us 14 carry 1, and that is nothing but 7. Is it clear? But you have to express it in form a plus, you have to find out what are a and b's. What are a and b's? So this is 5 upon 74 plus 7 upon 74i. Okay. So this is your, you have to find values of a and b. Okay. This is your a plus ib, implies a is 5 by 74 and b is 7 upon 74. Is it clear? Now we'll take few examples contributing other type of operations. So find AB such that, next example, a plus ib is into some complex number, say if I take 1 plus I is equal to some complex number, say 2 plus I here. A and B are real numbers. A and B are real numbers. So I want to find a plus ib, so we'll take 1 plus I on that side. Therefore a plus ib is equal to 2 plus I upon 1 plus I, which is equal to, multiply numerator and denominator by complex conjugate. 1 plus I into 1 minus I upon 1 minus I, which is equal to 2, then minus 2I, I minus I square, which is nothing but, and this is 1 square minus I square. But I square is minus 1, so we'll get 2 minus 2I plus I, that is minus I square is minus 1, so it is plus 1 upon 2, since I square is minus 1. So we'll get 3 minus I upon 2, which is nothing but 3 by 2 plus plus minus half times I. And therefore A is 3 by 2 and B is minus half. If your question is that find A plus IB, then keep this answer. Find A and B separately, then write A and B separately. Okay. Now take the example, express following in A plus IB form. Express 1 plus I into say 1 minus I its inverse in A plus IB form. So A plus IB is equal to 1 plus I into 1 minus I its inverse. 1 minus I inverse is nothing but 1 upon 1 plus I, so 1 upon 1 minus I. So it is 1 plus I upon 1 minus I multiplied by complex conjugate 1 plus I upon 1 plus I. Okay. Then this is nothing but 1 plus I bracket square upon, this is not 1 square minus I square, and this is nothing but 1 plus 2I plus I square upon 1 minus I square. Now I'll put value of I square here, which is minus 1. So 1 plus 2I minus 1 upon 1 plus 1, since I square is minus 1. And then this 1 minus 1 get cancelled and we'll get I. Okay, so this is your A plus IB form. A plus IB form. Is it right? So if I take one more example, express following as in form 3 plus 2I upon 2 minus 5I plus 3 minus 2I upon 2 plus 5I is equal to A plus IB. And therefore A plus IB is equal to, take the cross multiplication, 3 plus 2I into 2 plus 5I plus 3 minus 2I, 3 minus 2I into 2 minus 5I upon 2 minus 5I into 2 plus 5I. If you simplify this, what is 3 into 2? 6 plus 3 into 5, 15I plus 2 into 2, 4I plus 10I square. Okay, plus 3 into 2, 6, 3 into minus 5, minus 15I, minus 4I, minus plus, again 10I square upon 2 square minus 5I bracket square, and then this 15I, 4I, this get cancelled, and then we'll get this to be 6 minus 10 plus 6 minus 10 upon 2 square is 4 plus 25, since I square is minus 1, and then 6 minus 10 is minus 4 plus minus 4, that is minus 8 upon 29. Okay, so in this way it is too simple to solve examples on operations of complex numbers. So with the discussion, today we'll stop our session here. Try to solve examples from exercises, and if you have any difficulty, you can put that difficulties in comment box. Thanks. Bye bye.